Okay, good morning. Uh, so we're going to move on to the first sort of real chapter of the course. Although it may not seem like microbiology to you, it is a necessary skill that we need to review, and that is a general and basic understanding of chemistry. Now, why do we need to know chemistry to understand microbes? Well, because in understanding chemistry, we can actually devise ways of controlling their growth, directing their growth, maybe even eliminating their growth. So many of the chemicals that we use to either encourage microbes to grow faster so that we can make maybe insulin or some other human product that we have engineered microbes to do, requires an understanding of basic chemistry. But the same is true for pathogenic microbes. If we don't know how microbes reproduce at the chemical level, we don't have the tools to keep them from reproducing. Now, some of it is going to be more useful than other stuff, but I had to cover, everything from the basics of what is matter. So at the end of the day, when you look at an E. coli cell, just like these tables and the seats and everything else is made of matter, that E. coli cell is made of matter. Now, I'm drawing this in a very simple way, but there's a lot more going on here that we're going to talk about in a future chapter. Now I just happen to draw a double layer around that first circle, and this represents what we could call the cell wall. Now the cell wall has lots of chemicals in it. It has carbon, it has nitrogen, it has oxygen, it has hydrogen, etc. Now, I hope you had chemistry before, so you know that what I'm writing here are simply the chemical symbols for some elements. Now, what are elements? Well, the most fundamental kind of matter. And we don't have a periodic table, but the periodic table has all of the elements that exist in nature, plus then some. There are some elements on the periodic table that are human-made. We created in some sort of a nuclear reactor, but about 90 of them are natural. Now, of the 90, only about 20 appear in life, in living systems. And of the 20 or so, these are perhaps the most important. Now, what do these guys have in common? What is there in carbon that makes it, even though chemically it's very different from nitrogen, similar also to nitrogen? Well, that is actually what we're going to start this chapter with, and we're going to describe matter at the simplest level as being composed of atoms. So carbon is composed of carbon atoms, nitrogen is composed of nitrogen atoms, oxygen has oxygen atoms. Oxygen does not have carbon atoms. Now, how are they the same? Well, they are the same, and this is a cartoon. By no means this is the way real matter looks like. But in a cartoon that we're going to make here, we have a core at the center of this big space that sometimes is drawn like just a wavy circle around that core. Now, if you look in the internet, maybe even AI, you're going to see that they still draw atoms as having these elliptical circles around the center, the so-called orbits. Well, that's completely wrong as far as what we know now. The real picture is a little bit more like this, but this is still way off. So how big is the atom? Well, let me make a comparison to a real life object, if you will. Think of a football field. If you've never been on one, I apologize, and I'm talking about American football, but some of you have seen it, right? Maybe most of you. Well, it's a big space. I don't know, 100 yards by 100 yards, what have you. Now, if you imagine a golf ball Now, here we go again. What is a golf ball? But maybe most of you probably know that is a tiny, tiny sphere that some crazy people hit and chase in a golf course. My father included, by the way, but anyway. So a golf ball is about this size. If you put it in the center of the football field, that's the size of the core, and this space that I have drawn here is the rest of the football field. So the core is really tiny, tiny, tiny compared to the space that is making up the rest of this atom. Now, what is in the two areas that I just described? What is it found in the core, and what is found in this empty, big, huge space? Well, all atoms are composed, and this is very simplistic again, of three ingredients. So all atoms have protons, which is just the name of an ingredient of an atom. All atoms have neutrons, another ingredient. They're similar in some ways, they're different in others. I'll list those in a second. And again, hopefully this is just a review. And then there's a third ingredient in every atom called electrons. Now, there are more more ingredients to an atom, but they don't play a role in chemistry. They play a role more in physics, in nuclear physics. So we're going to ignore them. Photons and muons and positrons and a bunch of others don't matter here. What matter are these three. Now, how are they, comparatively speaking, similar and different from each other? Well, you need to remember that we're going to describe these ingredients in terms of a mass, but we're also going to describe it in terms of something that we're going to call electrical charge. And you really don't need to know much more than what you see on a battery. A battery has two poles, right? It has a positive end and it has a negative end. And when you're using a battery, if you're putting that battery, in a flashlight, you have to put that battery in the right orientation or it doesn't work. If you put it inverted, it just doesn't work. The positive end has properties that we call simply a positive charge or a positive end. The negative end has, comparatively speaking, the same type of stuff, but of opposite behavior, if you will. Maybe I made that more complicated than it should be. So positive is positive, negative is negative. There's a natural repulsion between positives and positives, and there's a natural attraction between positives and negatives. That's all you need to know about electricity. Now, we do have a symbol for the charge that is positive, and that is we use a plus sign. So protons are like the positive end of a battery. They carry this positive charge. Neutrons do not have a charge. So we're going to write that as a zero charge, neither positive nor negative. And electrons do have a charge, and that charge is negative. Now, for the purposes of this explanation, I'm going to give them an amount. So a charge of plus is always assigned to a number 1. So in other words, a proton has a charge of plus 1. Not plus 2, not plus 5, just plus 1. And again, you don't need to worry about how much, much more than that. The charge of a proton is plus 1. The charge of an electron is negative 1. In terms of electrical charge, you can see here that the electron has an opposite charge to that of the proton, and the neutrons carry absolutely no charge. They're neutral. Now, we need to talk about mass. How heavy are these particles? Once again, comparatively speaking, we're going to compare them to each other. And for the purposes of this discussion, we're going to say that protons weigh 1. And I can give you the units, but it doesn't really matter. They're called AMUs, atomic mass units. The neutrons have about the same mass. They weigh about the same as the protons. So they have a mass of 1. Now here's the thing, for this course, and for many of my chemistry courses I actually do the same. The electrons weigh or have a mass of 1 divided by 2,000, the mass of the proton. So 1 divided by 2,000 AMUs. If you divide 1 by 2,000, you're going to get a very tiny number, right? 0.000 something, 0.0005. Well, to make things very easy and straightforward, because we don't need to know much more than that, we're going to imagine that the electron has no mass. That's really not true. You know that it's 1/2000th of a proton, 1/2000th of a neutron. But to make our math and our calculations easier, we're just going to say, oh, they weigh basically nothing. We're going to neglect it. Okay, so now these are the properties of the 3 ingredients that make every atom, as far as charge and mass is concerned. How are carbon, nitrogen, oxygen, and hydrogen different from each other? Well, by the number of these ingredients that each of those different chemicals have. So if you look at the periodic table, you're going to find out that carbon shows up there, and often is written as follows. So the symbol for carbon is C, and then you see that they have 12 on one corner of the symbol and a 6 on the other corner of the symbol. That's roughly speaking how we write these chemical elements using shorthand notation, symbols. Now, what is the difference between the 12 and the 6? Well, let's first define this number, the smaller number of the two. The smaller number of the two refers to the number of protons found in an element. So one carbon atom happens to have 6 protons. Now the protons are located in this core, which I'm going to have to make a little bit bigger, but you know that it's actually tiny. So if this is carbon, there are 6 P's there, 6 protons. Now, once again, at the beginning of this discussion, I need to set some rules. And the rule is going to be, the next rule is going to be that the number of electrons in every atom, as we speak right now, is going to be equal to the number of protons. So this carbon atom is going to have 6 electrons. Now, the electrons are not in the nucleus. The electrons are sort of spread out, and I'm drawing them as a cartoon, as little dots, 1, 2, 3, 4, 5, 6. So there are 6 electrons there on one single carbon atom. So these are my cartoon indicating electrons. But they're not in the core. They're still negatively charged. And comparatively speaking, they're very, very, very tiny, 1/2000th of the size of a proton. Now, what about the left, the one ingredient that we haven't mentioned? Well, in this particular case, for this particular carbon, the number of neutrons happens to be the same as the number of protons. So there are 6 neutrons. It's not always the case, but in this particular situation, it happens to be the same. So we have 6 protons, 6 neutrons, 6 electrons. And the 6 protons correspond to this number. Now, listen carefully, please. The number of protons of any element is the ID of the element, is what identifies the element as X, Y, or Z. So if an element has 6 protons, it has to be carbon. There's no other element with 6 protons. An element can have the same number of neutrons as the number of protons, or it can have more, or it can have less. So let me write another symbol for another type of element. Now this is a C, right? So it's another carbon. So the number of protons better be 6. Now this number up here, now I'm going to write it as 14. So what just happened? Well, it turns out that this number on the top is actually the sum, simple arithmetic, of protons and neutrons. So 6 plus 6 is 12. That's the number of that you see here. Now, in this case, guess what? Well, we still have 6 protons because otherwise it wouldn't be carbon. But if I were to copy that over here and draw the core and then the cloud, this to be carbon still has to have 6 protons. But in this case, to get this 14, I need to account for 8 neutrons. So that is still carbon. It's a little bit fatter, heavier, but it's still carbon. And in fact, we call them a heavy isotope. So these two guys are isotopes of each other. So that's a name that you don't need to remember, but it's useful because sometimes you use these terms even in allied health. If you're in a hospital and somebody is receiving chemotherapy, you may hear the word ruthenium radioactive, which is an isotope of ruthenium that happens to be radioactive. At any rate, my point right here is that both of these are carbon because both of them have 6 protons, but one is a heavy carbon compared to the other one because it has more neutrons. What are these numbers called? Well, they do have a name, and I haven't asked you any questions today. I just want to get through this without boring you too much. So that number is simply called the atomic number. Atomic number. And it describes the number of protons. This number has several names, but we're going to call it the atomic mass. You may hear something like the molar mass, the molecular weight, the atomic weight. There's several names, but we're going to just simply call it the atomic mass. And the atomic mass is the number of protons plus the number of neutrons. This is just the number of protons. Now, when all is said and done, the protons and the neutrons determine the nature of the element and how heavy the element is. But it is the electrons that determine how happy or unhappy an element is, how reactive. So some elements are super happy the way they are. Carbon is somewhat in the happiness scale happy. Some other elements are super unhappy the way they come in nature. So they are always seeking partnerships to become happy. They're looking for a partner to live their lives not so unstably, reactive. So I'll explain that in a minute in probably a better way than my bad example. But any questions so far about the basic identity of these elements? So what if I were to write here, instead of that, I have something from the PowerPoint presentation. I have oxygen, and I have a 16 here and an 8 there, and then there's a couple more. I'm just going to copy one more. So those two represent oxygen atoms. They're isotopes because they have a different mass number or atomic mass. They're both oxygen because they have both of them 8 protons. The periodic table shows you the identity of the atoms based on the atomic number. So if the atomic number is 8, it's oxygen, 8 protons. If the atomic number is 6, it's carbon, 6 protons. If the atomic number is 1, then it's hydrogen. This is the lightest of all elements in nature. Now, I mentioned carbon already, oxygen now, and hydrogen. These are very, very important in biological systems. Now, there's one hydrogen that actually has a mass of 1, another hydrogen that has a mass of 2, and another hydrogen that has a mass of 3. So Here are 2 isotopes of oxygen. Here are 3 isotopes of hydrogen. Chemically speaking, those are indistinguishable. They're identical. So you can have water. Anybody remembers the formula, the chemical formula for water? H2O. Don't be shy, H2O. Now, we're going to talk about chemical formulas very briefly also in a few minutes, but H2O, water, contains hydrogen and oxygen in that proportion that you see there. There's actually one here that we never write. Whenever you don't see a number in a molecular formula, that means that there's a 1 there. But this water can have this type of hydrogen, or it can have this type of hydrogen, which we would call heavy water because it is heavier. And then the heaviest water would have this guy. Now, these are found all in nature. This is found in nature, this is found in nature. But some of these elements are found in more abundance. And if you're guessing that hydrogen of this type is the most abundant of all the hydrogen in the universe, you would be right. There's very little heavy hydrogen and heaviest hydrogen. That's a lot of these. 99.9% of all hydrogen is like this. Why does that happen? It doesn't matter in this course. They are the result of natural transformations that take place in these atoms. In the case of oxygen and 16 and oxygen 18, the proportions are also favoring this one. There's less of that than that. There's also oxygen 17. Now, very quick pop quiz. How many neutrons are in this hydrogen? 2 neutrons. And how many protons? 1. 1 proton, 2 neutrons. The 1 proton is always at the bottom. If you can think of this as a top-heavy element, written as top-heavy, you put the heavy number, the large number on top. You see that represents the 1 proton. This represents the 2 neutrons plus the 1 proton that you just mentioned. 2 plus 1, 3. So how many protons are in this element? Protons, 8. And how many neutrons? So 18 minus 8 is 10, so there will be 10 neutrons. Okay. Now with that in mind, we can actually write the symbol of any element and know how many protons we have and how many neutrons we have. But I haven't mentioned the electron. And the electron is actually responsible for making elements be happy or unhappy. And let me start simply, well, we're going to go to water just because water is a good example to learn about the happiness of elements. So in this symbol of water, the little numbers on the bottom do not represent number of protons, do not represent number of neutrons. These actually represent number of hydrogens in 1 unit of H2O. So 1 water molecule, 1 water unit, has 2 hydrogens, and it has 1 oxygen. For every 2 hydrogens, you have 2 oxygens. How come? Water is super stable. If you leave a glass of water here today and you come back next month, well, maybe there'll be a little bit less water because it's evaporating, but chemically speaking, it's still water, it's still H2O. Super stable. If you find hydrogen in nature, it's not very happy. It's always exploding. It's always blowing up. So hydrogen in nature happens to have, most of the time, that configuration, right? 1 proton, no neutrons. Well, if I make that into a cartoon like those, I'm going to draw the core with 1p, and in the cloud, I'm going to put 1 electron. So that's hydrogen. Now, if you imagine 2 of those, if you imagine 2 hydrogens, the second hydrogen would be identical to the first. So you have this core, and then this 1 electron. This guy is explosive in nature, not very happy. This guy is explosive in nature, not very happy. It turns out that when the two are in the vicinity, they realize that they can become happy, in my silly explanation, by doing something to those electrons. So what happens is the following. They overlap. They come very close to each other. And they pretend to each of the two hydrogens, which are still one proton, they pretend to have two electrons around them. So this one hydrogen realizes that there's another hydrogen nearby with an electron that is not very happy, and it overlaps with it. In that overlapping, now you have this bigger cloud that for each hydrogen has essentially two electrons. This is called a duet. So two. And elements like hydrogen, there's a couple of others, but we're not going to bother. Elements like hydrogen are super happy when they have a duet, when they have two electrons around themselves. If they don't have two electrons, they're not happy. They're explosive. But once this happens, you have something called hydrogen gas. It's still kind of reactive, but it's happier than the hydrogen with only one electron. So H2 is called hydrogen gas. And it's an element that you find in the atmosphere. Now, fine. So this is somewhat happier than hydrogen by itself. The two hydrogens are together. Can we actually make hydrogen even happier than just having two hydrogens around? Well, let's take a look at oxygen in water. Oxygen at the core has 6 protons. Wait a minute, no, 8 protons. And it has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now, notice that I just sort of hesitated, but I tried to make a point that 2 of the 8 electrons are closer to the nucleus. If you didn't notice that, I'm telling you right now. I tried to make these 2 electrons being a little bit closer to the nucleus. Well, here comes the reason. I'm going to draw a cartoon a little bit differently. Here is a core. Here is one circle. Here is another circle. These 2 circles are still the same cloud that I put here. These 2 circles are still representing all of the electrons on oxygen. However, we now know that electrons actually like to be as close to the nucleus as possible with some limitations. There's not enough room for every electron to be close to the nucleus. And the not enough room is explained in the following way. Very close to the nucleus, we have an orbit, a cloud, that can accommodate 2 electrons. There's no more room than space for 2 electrons. And that happens to be the case for hydrogen too. I didn't mention that, but now you see that this guy is looking always for a duet, for 2 electrons. The reason is because very close to the nucleus, there's an area which we could call an orbital, we could call a cloud. The point is that that area can accommodate 2 electrons, and that's when the space for electrons there is fulfilled or filled up. Now, there's another space, not as close to the nucleus as the first one, but still close enough where the other electrons of, in this case, oxygen are going to be found. So there's 1, 2, 3, 4, 5, 6 electrons. Those are found in the second layer. And it turns out that that second layer, and for this course only, every layer after that has space for 8 electrons. So there's space for 8 electrons here, but there's only 6 of them, right? 1, 2, 3, 4, 5, 6. There's a space here for another one. There's a space there for another one. That's still oxygen because there's 8 protons there. Well, if we imagine that being the case, and I go back to my original drawing of the hydrogen, two hydrogens, each hydrogen with one electron floating around the periphery. Not happy, not happy, actually not very happy either. When now, instead of those two find each other, these two find this guy, something very interesting happens. This electron on this one hydrogen is going to come very close to this space. So it's going to overlap. One proton, and then the cloud is going to overlap. The one electron here is going to feel the presence of these 6 electrons, and it's going to say, well, I want to be in that space. So I'm going to send my electron to spend a lot of time in that neighborhood. Same thing for this guy, for the second hydrogen. So you have one proton, you have this cloud with the one electron of hydrogen hovering there. Now, without going into too much detail, this situation generates the following. It gives oxygen 8 electrons, which is what they want. The second level, the third level, the fourth level where electrons reside can accommodate 8 electrons. We call that an octet instead of a duet. But importantly, this hydrogen, which is sharing this electron, is also sensing the presence of the other electrons. And it's happy because it feels like it has 2. Now, that was a long explanation for something that should have been maybe a review for you, but maybe not. Let me simplify it a little bit. Well, I'm going to simplify it a lot, and then I'm going to go back and add some details. So I can draw water as follows. I can draw one hydrogen there. I can put an oxygen there and another hydrogen here. And then I can join the hydrogen and the oxygen with a dash, with a long line. And then I can do the same for this oxygen and this hydrogen, join them together. Whenever in chemistry you see a drawing like that, and you probably see it a lot, that dash represents one pair of electrons. Is this one electron plus one of these guys? Okay? So one dash represents 2 electrons. So 2 electrons. This dash, same thing, a pair of electrons. So hydrogen, by sharing that one electron with one of the electrons of oxygen, feels that it has a duet, right there and right there. Now here's the interesting thing about oxygen. So if we count these electrons, and we count these electrons, we don't have the same number. So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Here we have 1, 2, 3, 4 electrons. There's 4 electrons missing, right? That I haven't accounted for in this drawing. Well, sometimes you may see them in molecules written as follows. 2 little dots here, 2 little dots there. Those guys are these other 6 electrons. 1, 2, 3, 4, 5, 6. These 2 plus those 6 make the 8. So those 2 electrons and those 2 electrons plus these 4 electrons give you the 8 electrons, the octet. Now these have a name. They're called lone pairs of electrons. So there's 2 electrons, 2 electrons. When you draw them like that, you know that you have a pair that is separate from the rest. So there's one, there's another one. So now we have completed a picture of water in which, in a way, I'm trying to explain to you the role that electrons have in chemical reactivity, in combining with other elements. So one oxygen combined with 2 hydrogens to form a very stable entity that we know as water. And this is more or less how we visualize it. It's a cartoon, right? But it explains things in a kind of a nice way. We can account for the 8 electrons of oxygen. We can account for the 2 electrons of each hydrogen. If we count electrons total, we haven't added or subtracted. We have just the same that we came with at the beginning. 1 for each hydrogen, 6 for each oxygen. Okay, so I know I'm making things a little bit more complicated now, but I need to add another layer of complexity. I need to give you some, or remind you of some names, and then point out some features of these different chemicals. So I'm going to go back to the hydrogen, oxygen, hydrogen drawing. But this time, I'm going to introduce one concept that may be new to some of you, may be a review. And that is something called electronegativity. In plain English, this is an electron greediness. How greedy are certain atoms for electrons? I have simplified this quite a bit, but I'm going to add one level of complexity here. It turns out that when this hydrogen is feeling the 1 electron from this oxygen and is getting happier because it has now 2 electrons around its own core, it doesn't have the greediness that oxygen has for that 1 electron that is being shared. In other words, oxygen is more electron greedy than hydrogen. I would say that in terms of chemistry, oxygen is more electronegative. So even though this pair of electrons is being shared, it's not being shared equally. The electrons spend more time closer to oxygen than to hydrogen. That creates a situation known as a polar bond. So this bond has polarity, has a positive end, and it has a negative end. If the oxygen is more electron greedy, then the electron is going to spend more time close to the oxygen, which is going to make this more negative. We indicate that with an arrow. The head of the arrow points towards the more electronegative element. In this case, oxygen. So oxygen is more electron greedy, hydrogen is not as greedy. The 1 electron that hydrogen is contributing to this partnership spends more time closer to the oxygen than to the hydrogen. If I want to make this even more clear, I can actually cross this end of the arrow like that. And this almost resembles like a positive sign if I put a circle around it. So when I indicate a sharing of electrons with an arrow, I'm basically telling you that you have a bond that is polar. So the same happens in this other bond. This oxygen is more electron greedy than this hydrogen is, so the electrons of the hydrogen, the 1 electron of the hydrogen spends more time around the oxygen than around the hydrogen, creating a polar bond. Now what is a bond? It's chemical glue, right? It's this cement or glue that joins atoms together. And this type of glue in particular is called a covalent type of glue. So to complete the picture, each bond in water is said to be a polar covalent bond because there's a difference in greediness for electrons between the oxygen and the hydrogen. Okay, so is that always the case? So I'm going to draw some examples here of other molecules that may be somewhat important in biology. So for instance, let's draw here trust me when I tell you that this is called methane. Okay? Now, trust me when I tell you, and I'm drawing another chemical here. Let's go with a chemical called isopropyl alcohol or propanol. This is rubbing alcohol. Propanol. This is called methane. Well, using the basic rules that I just described to you for the past few minutes, I can actually draw something similar to the water formula using symbols. So I'm going to first draw methane. I'm going to have carbon here. I'm going to join carbon to each of those 4 hydrogens with dashes. Every dash represents a pair of electrons. And I'm going to put a hydrogen at the end of every dash. So this guy and this guy are the same, except that this shows more detail, right? Now, you already know that hydrogen has 1 electron. It has 1 proton, and it has 1 electron, right? We knew that from the previous discussion. It has an atomic number of 1, so it has 1 proton, and it has 1 electron. Now, the 1 electron here is not happy, so it's looking for electrons elsewhere, and it finds 1 in carbon. And they share a pair. Same thing happens to the other 3 hydrogens. Now, what about carbon? I think I had it written earlier as having that configuration. 6 protons, 6 neutrons. If it has 6 protons, it has 6 electrons, right? Now, where are the 6 electrons of carbon? Well, the first 2 are in that inner area that forms a duet that are not going to be important for this description. What are going to be important is, so if I draw carbon here, here is the center with the 6 protons, and then I have my first cloud, I have my second area of electrons. In the first there's 2. Well, there's 4 left, so there's 1, 2, 3, 4. 4 electrons plus 2 is the 6 electrons that carbon has. But of the 6, 4 are on this outermost area. 4 is not going to make carbon happy. Carbon has to get 8, just as oxygen did. So the second layer is complete, is happy when it has 8 electrons. So carbon has to look for 4 electrons somewhere. Well, 1 electron from that hydrogen is going to make carbon have now 5, plus 1, 6, plus 1, 7, plus 1, 8. So now we have this scenario in which 1 carbon is sharing 4 electrons, 1 each, with a hydrogen. These dashes, just as before, represent a covalent bond. So that's a covalent bond. And it's a pair of electrons. There's 2 electrons. Now, unlike water, where you have these 2 lone pairs, let me put the name again. Carbon doesn't have that, because each one of the each one of the electrons that carbon has is being shared with each one of the electrons of hydrogen. That makes this carbon have 8, and there's no leftover electrons, right? Moreover, the greediness of hydrogen and carbon for electrons, the electronegativity of hydrogen and carbon, are about the same. Oxygen is very electron greedy. Carbon is not. Hydrogen is not very greedy. It's about as greedy as carbon is. So this bond, unlike this bond, is said to be nonpolar, because the sharing of the electrons is about equal. And that is due to the fact that the electronegativity of carbon and the electronegativity of hydrogen is about the same. Does that make sense a little bit? So we call bonds between elements that have similar electronegativity nonpolar covalent bonds. And I'll give you some rules before we finish with this discussion. We call bonds in which one atom is more greedy than other polar covalent bonds. Okay. We have propanol left to draw in a way that explains some of the chemical properties of propanol. Now let me erase this for a second and give you a simple chart of electronegativity. It's actually quantifiable. You can actually assign a number, but not in this course. In this course, we're just going to talk about being the same or being different. Carbon and hydrogen are about the same when it comes to greediness. Greed for electrons. So every time that you see a bond between carbon and hydrogen, it's going to be a non-polar bond. Oxygen is more greedy than hydrogen and carbon. Nitrogen is more greedy than hydrogen and carbon. Now, we're not going to compare oxygen and nitrogen too much because we don't need it. We don't need to, but there is a difference between the two. One is a little bit more greedy than the other. Now, with these four elements, carbon, hydrogen, oxygen, and nitrogen, we can form a lot of molecules that are going to have biological importance, and you're going to see them very soon. But just remember this simple rule. Carbon and hydrogen are about the same when it comes to greediness, so every bond that you have between carbon and hydrogen is going to be nonpolar. Oxygen is more greedy than carbon and hydrogen. Nitrogen is more greedy than hydrogen and carbon. Therefore, those bonds are going to be polar. Bonds between oxygen and carbon, polar. Bonds between oxygen and hydrogen, polar. Bonds between nitrogen and carbon, polar, because nitrogen is more greedy. Okay, so let's put together this molecule and explain a couple of features about it. So I'm going to blow it all up. I'm going to show every bond that exists in this somewhat longer molecule, but still a very short one comparatively speaking. So we have one carbon connected to another carbon, connected to another carbon, 1, 2, 3, and then connected to an oxygen. This carbon is this carbon right here, and it has 3 hydrogens connected to it. So there's 1, there's 2, there's 3. Hydrogen, hydrogen, hydrogen. So that represents this CH3. This carbon has 2 hydrogens connected to it. 1 and 2. This carbon is also connected to 2 hydrogens, so it's connected to 1 and 2. Now, I haven't explained the fact that this carbon is also connected to this carbon, but I'm representing that with that dash. So this carbon and that carbon are connected by that covalent bond. Just as this carbon and this carbon are connected by that one, and this carbon and this oxygen are connected by that one. We have one more hydrogen to place in our cartoon. I'm going to put it right there. And we're almost done. Now let's count atoms. So we have 1 carbon, 2, 3 carbons grand total, right? We have 1, 2, 3 carbons grand total. We have 3 plus 2, 5 plus 2, 7 plus 1, 8 hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And then we have 1 oxygen only. The 1 oxygen is right there. Now, if we count electrons, each hydrogen better have 2 electrons. And those are represented by the dashes. So that dash connects this hydrogen to this carbon. That's 2 electrons. Check. 2 electrons. Check. Same thing for everything. If you notice, every carbon has how many dashes around it? Count the dashes. So how many dashes, how many bonds are between this carbon and all of the atoms that is connected to? 1, 2, 3, 4 dashes only. So that represents 8 electrons, the so-called octet that carbon is always seeking. So 2, 4, 6, 8 electrons, that carbon is complete. Whenever you draw molecules like this, every hydrogen needs to be connected to something else with 1 dash. Every carbon has to be connected with 4 dashes to something else. 1, 2, 3, 4 for that carbon, 1, 2, 3, 4 for that carbon. Now oxygen, just like in water, we had water like this, needs 2 bonds. And there they are, 1 and 2. But we're not done because we know that oxygen has 8 electrons, just as carbon has. This carbon has 8 electrons. However, the 8 electrons are all busy in this glue, in these covalent bonds. The electrons of oxygen are not all busy in bonding. There's only 4 of them, 2 plus 2, 4. So we need to indicate that there's 2 more electrons by drawing those 2 pairs of dots as lone pairs. So now we have a lone pair of electrons here and a lone pair of electrons there. Now we're almost done. What type of bonds are these compared to those? Well, based on the greediness, anytime that you draw a formula in this way, the bond between a carbon and a hydrogen is always going to be nonpolar, because the greediness of carbon is about the same as hydrogen for electrons. So nonpolar bond, nonpolar bond, nonpolar bond, so on and so forth. Now, here we go. We know about this bond already because of water, right? We know that hydrogen is less greedy. We know that oxygen is more greedy. So we indicated that earlier with an arrowhead pointing to the oxygen, right? That arrowhead means the oxygen is more greedy for electrons. And if we want to be super, super detailed, we can put a cross like that, meaning this is like the positive end, this is like the negative end of that bond. So I want you to take a guess as to that bond, this dash. Based on these rules that I wrote, is this bond polar or non-polar? Polar. Based on this rule, oxygen is more greedy than carbon. Now here the carbon is sharing an electron with this oxygen, but the oxygen is more greedy. So if I wanted to indicate that, I would have to indicate that with an arrowhead. So that is in fact the case. That's a polar bond. Okay. We're making lots of progress in very little time, so I am so sorry for making this, such a complicated thing, if you will, but it's a necessary complication. It's a complication that is going to make you make connections and see things that are sometimes not readily visible until you understand some of these rules. So, methane, if I draw it again, has absolutely no polarity. All of this glue is nonpolar, right? We already said that. Propanol, or rubbing alcohol, well, let's break this molecule apart. It has like this area. This part of the molecule has all nonpolar bonds, right? All of those are nonpolar. So this part of the molecule is nonpolar. But we're not done because this molecule has more going on. It has this oxygen and this hydrogen, this OH group. This is actually, it has actually a name. It's called a hydroxyl group. We're going to review some of them very shortly. So there's more going on here. This part of the molecule is polar. So propanol is both nonpolar and polar. Okay? Now, let's bring water back to the picture. We have hydrogen, oxygen, hydrogen, and we said that this is a polar molecule. So this molecule is polar. And I promise you, this is the last complication I'm going to add. I know it's overwhelming. So these arrows indicating that there's more attraction of the electrons by this oxygen than the hydrogen creates the following poles. We're going to introduce a new symbol, the Greek letter delta. It has like a D in the Greek alphabet. And on top of the hydrogen, I'm going to put a delta plus, meaning the following. Partial positive charge. And by partial, I mean it's not a 1 plus. Remember that we started this discussion saying that the protons carry a charge of 1 plus. Well, this hydrogen does not carry a charge of 1 plus. It carries a charge of less than 1 plus, which we're going to call it a partial charge. It's not quite 1, but it's more than 0. Does that make sense? So there's a little bit of polarity there. These two pairs of electrons that are non-bonding, both of them are going to have a delta, but it's going to be now a delta minus. So this oxygen has two centers, if you will, two areas of partially negatively charged. This is partially negatively charged because of those two electrons. This is partially negatively charged because of those two electrons. And if your guess is that this hydrogen is going to have also a partial charge, and you guess that is positive, you're right. Just as this hydrogen, this is partially positively charged. Now help me out. Are there any partial positives or negatives in methane, in CH4? Do we have a partially positively charged hydrogen or a partially positively or negatively charged carbon? The answer is no. Why? Because the bond is nonpolar. If there's no polarity, you cannot have a partial positive or a partial negative. To have a partial positive, you need to have a polar bond. To have a partial negative, you had to have a polar bond. Okay? So this guy has no polarity anywhere. This is completely nonpolar. There's no electrical charges showing up there. We're going to leave it like that. But let's go back to this one. The nonpolar part of isopropanol, or of propanol, if you will, has no charges. No charge here, no charge there. But now let's label this one. This one is going to be labeled sort of like water. The hydrogen, partial positive. This carbon, partial positive. These two pairs of electrons around the oxygen, each of them partial negative, partial negative. Again, when I draw that letter, the D in the Greek alphabet, what I meant to say is that it's less than 1, but there's still a charge. So here I have a question for you. If this is all surrounded by partial negatives and partial positives, is this going to feel any attraction for this that has no charge? The negatives attract the positives always. Remember that rule. So if you have a positive charge here, even if it's partial, and a partial negative charge here, they're going to feel an attraction for each other. They're going to try to pull each other together. There's no partial positives or negatives here. But there is partial positives and negatives there. Is there going to be an attraction between those two? The answer is no. Because there's nothing here to attract this partial positive or that partial negative, right? This is completely neutral. How about this feeling an attraction for this molecule? Well, as a whole, water is not going to like to be on this area because there's no attraction. There's no positive or negative charges here, partial or otherwise. Over here, you have partial positive, partial negative, partial positive, partial negative. So water is going to feel that attraction. So water is going to feel a certain attraction for propanol because of this part of the molecule, not because of that part of the molecule. How do we represent that? Well, I actually can put water in the vicinity partial positive, partial positive, partial negative, partial negative. So this partial negative is feeling this hydrogen and it's been attracted to it. With that wavy line, I'm trying to represent an attraction, an electrical attraction between this negative part of the water and this positive part of this alcohol. Sorry, I just called it an alcohol without telling you, but that's an alcohol. Anytime that you see an OH by itself connected to a carbon, you have an alcohol. So that attraction has a name. I know this is a lot of information for one session, but that name is a hydrogen bond. It's another type of chemical glue, not as strong as the covalent bond. The covalent bond is very, very strong, but it's nevertheless real. There's a positive charge here that feels a negative charge there. They attract each other, and they form this attraction. Well, guess what? We know that oil and water don't mix, right? Or if they mix, they separate. If you combine oil at home with water and you shake it, it's apparently combining, but then it separates. That's because there's absolutely no electrical attraction between the oil and the water. Oil is non-polar, water is polar. If I were to mix methane with water, they would separate. Why? Because methane is non-polar and water is polar. What do you think will happen if I mix this with water? Well, they're going to mix a little bit. Although this part doesn't like water, is what you probably remember calling hydrophobic, this part likes to mix with water. So it's hydrophilic. It likes water. So propanol is going to mix with water a little bit, not as well as water with water, but it's going to nevertheless mix a little bit. Now, to see if I'm making my point, let me ask you a question here, and this is hypothetical. I'm going to give you 3 molecules here. So that's a real molecule. It's called methanol. This is another real molecule. It's called ethanol. So this is methanol. You're probably beginning to see the pattern. Anytime that you have an OH, you end up naming the molecule with OL, which means an alcohol. Ethanol, in case you don't know, that's what is found in beer and wine. That's what makes people like it and get a little kind of crazy when they drink too much of that. It's actually an alcohol that is making you, let me say it this way, intoxicated. Now, there you have ethanol. The one that I had before, called propanol, And then I'll put one more for good measure. CH3, CH2, 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 1, 2, 3, 1, 2, 3, 4, OH. This is called butanol. And by now, you should be able to, in the peacefulness of your own, study session, know that this, that, and that is nonpolar, right? And you should know that this, and that, and that, and that is polar. So polar, nonpolar. And here comes a thinking question. What do you think is going to mix with water more, better, and which one of these is going to mix with water less happily, less well? Which one is more soluble in water, mixes with water better? You can take a wild guess or you can take an educated guess. Think of water being polar and liking to mix with polar parts. So all of them are going to mix with water, right? Because that's polar, that's polar, that's polar, that's polar. But the problem is that this has more nonpolar than this. So these are about equal. This is a heck of a lot more nonpolar than polar because this is a long, long chain of carbon compared to this single carbon. So which one do you think is going to mix with water better? The methanol. And that is indeed the case. If you look it up, if you do use AI and you look for the solubility of methanol in water, the solubility of methanol in water is going to be higher than this. And as you keep adding and adding more and more carbon, the solubility, the ability to mix with water, goes down because there's more nonpolar than polar. Okay? Oil does have a little bit of polarity, but it's so little compared to the, so oil, most oils, olive oil, canola oil, all of those guys, are like what I just drew here, but they have a CH3 at the end, and then they have this CH2 about 20 times. So there's 20 of those. CH3, CH2, 20 times. And then finally, not even an alcohol, but it's another group that we'll talk about in a second. Like that. That's still a little polar. But the huge number of carbons that are present in olive oil or canola oil make this molecule very much insoluble in water. It cannot mix with water because it's very, very much nonpolar. There's very little polarity. Okay, let me slow down a little bit. And of course ask you, are there any questions? I think when you look at the homework, you're going to find out that maybe I went overboard with some of the explanations, but some of the questions are going to be fairly straightforward to answer once you understand some of these basic principles. Now, the chapter is a little bit longer than that, so we're not going to finish it today. I'll probably finish this next Wednesday. But the next part that we're going to talk about is something called functional groups. And I'm going to leave you with an idea here. About something called macromolecules. I'll give you the name of some families of macromolecules. So names of macromolecules include carbs, fats, and proteins. These, comparatively speaking to what we have talked about, are huge molecules. Therefore, the word macro. Water has 3 atoms, right? 2 hydrogens, 1 oxygen. So it's a molecule with 3 atoms total. Carbs have thousands of carbons and hydrogens and oxygens. So these are big, comparatively speaking. Now, all three of these are combined by using smaller molecules, some of them carrying something called functional groups. And what we're gonna start talking about on Wednesday is the following functional groups. You already know one, it's called the hydroxyl. It's an OH group. To that, we're gonna add the carboxyl, the aldehyde, the ketone, the amine, and finally something called the phosphate. We'll explore them on Wednesday, but that's where we're heading. All of these functional groups are gonna be found in these big, big molecules, and you're gonna be able to recognize them. Every time that you see an OH at the end of a molecule, you know you have an alcohol. Every time that you see something that resembles a carboxyl group, I'll give you a heads up, carbon double bond O, OH. This whole thing is called carboxyl.